Okay. So we have discussed till now complex power, transmission capacity, then bus admittance matrix and power flow equation. So far we have formulated the power flow equations, right? So far we have formulated the power flow equations, right? So today we will see from this moment onwards next 4 classes. So 4 classes we have discussed about transmission capacity, complex power and power flow equations. Okay. The rest of module 1, 4 classes we will discuss about the solution of the power flow equations. Okay. All 4. One class will devote the easiest method, the Gauss-Siedel method. Then 2 classes on Newton-Raphson method, which is the most widely used. And finally the last class will be on first decoupled method, which is the approximate method. Okay. For all the methods you have code in your power system lab. Those will perform this load flow experiment. They will see the code for all these methods. Okay. Gauss-Siedel, Newton-Raphson, okay, fast decoupled, all code is there. You need to understand that. We will discuss the code here. Okay. So we'll move to Gauss-Siedel method. Gauss-Siedel method of power flow solution. The Gauss-Siedel method is also known as the method of successive displacement. Okay, so how the Gauss-Siedel method works? Ideally, in engineering course, you are supposed to read numerical methods in one of the mathematics papers, where you will be introduced to various iterative methods like Newton-Raphson, Gauss-Siedel. Okay, if you have not read, we will see this basic example how Gauss-Siedel method works. It's an iterative method. As I discussed in the last class, we start with a guess, an educated guess. Okay, we start with an educated guess, then we iterate until there is no significant difference between successive iterations. Okay. Consider the solution of the non-linear equation given by fx is equal to 0. Write down. So just write down fx is equal to 0. Okay. This is the equation. This is your first equation. Step 1. Second, you write this equation as x equals to gx. Okay. You write this equation in this form. Okay. Third, you give an initial estimate, okay, which is xk. Okay. So this is third. That means the first estimate will be x0. Zeroth iteration. Zeroth iteration. No iteration is still being made. So that is the first iteration. Zeroth iteration. Okay. Then in the next iteration, you will find the value of x using this formula. And finally, you are going to stop when the value between successive iterations is below a certain threshold, which is known as the tolerance level. So tolerance may be say 0.001. So that depends on your requirement. Okay? That depends on your requirement. So all of you write this 4 steps. Only write the 4 steps, not the details. Okay? Write the 4 steps, not the details. We'll solve one problem on this. Okay? Done? Done writing all the 4 steps, not the details. Just write whatever I have written as 1, 2, 3, 4 and 5. So there are 5 steps. Done? Okay. Next example. Now, first step was writing one equation fx equals to 0. So this is the equation. This is 1. Okay. This equation 3 is actually part step 1, where you have written the equation in the form of fx is equal to 0. And this is 2. This is 2, where you have written the equation in terms of x equals to gx, another function, where gx is equal to this one, minus 1 by 9 x cube plus 6 by 9 x square plus 4 by 9 is equal to gx. Okay. Write it down. Okay. Did you write? So first you have to write in terms of fx equals to 0, then x equals to gx. Okay. But what was the third one? That we start with an initial guess. As you can do a simple problem, so we start with x0 equals to 2. You could have taken any solution. Now, but it is an educated guess because you will say I will take 99999 as my first guess. Okay, you can start with that, but then you have to make more iterations. Okay, to reach the result. Okay, so you have to estimate something which is near to the solution, appears near to the solution. So start with 0 equals to 2. Now x0 is 2. What is x1? What was the equation you have written? G of x0. Is it? Step 4 you have written. So it is g of x power 0. X k plus 1 is equal to, you have written x k plus 1 is equal to g of xk. Is it? Did you write this? So that means x1 is equal to g of x0. So what is g of x0? Simply you will put 2 here. Okay, 2 here. Here, instead of x, you are going to put 2. So what is that? x1, what is x1? Calculate. What is x1? Compute. That means you are computing minus 1 by 9, 2 cube, plus 6 by 9, 2 square, plus 4 by 9. Okay. So you should get 2.22. Did you get that? Solve. Solve, you should get the first value. It x0 equals to a guess. The initial guess. That's here you can start with 3 also. No problem. x0 equal to 2 is a guess. You can start with anywhere. Yes, for example, you have taken. Did you get 2.22? As you want. Now what is x2? x2 means iteration 2. Value of x in iteration 2. What is x2? x2 is equal to g of x1, right? Now what is x1? G of 2.22, right? So compute again. You should get x2 equals to 2.5173. Just do this only. Okay? Just compute x2. Value of x in iteration 3s. Which other thing? Okay, you are talking about the other solutions. No, we are not bothered about this. Okay. So yes, one solution. Because we have taken the initial guess like that. See, he asked a very nice question. It's a very good question. Okay, he asked that here we are only getting one solution. It is a cubic equation. Okay. So we can get 3 solutions also. He says that. Okay. Now the point is that if you start with a different initial guess, you might get a different solution, which can be wrong, which happens most of the time in power systems. So you gave a wrong initial guess, you get somewhere which is actually correct, but then it is not a feasible solution. Okay, it's not a feasible solution. Now, by chance, we have taken a very near to a feasible solution. We have taken our initial guess. Suppose we have taken something. Suppose this solution has some other result solution which is far away from this solution. That is also possible. So that means as his answer is that, the answer to his question is that if you start a different initial guess, you might get a different solution. Okay. But then we should always check whether the solution is feasible or not. Okay. Okay. So did you get this? So we'll stop there. So then accordingly you will continue with x3, x4 and so on till the difference between, what is the difference between 2.51 and 2.22? It's much larger, so 0.3 something like that. Generally you get a tolerance of 0.001, 10 to the power minus 3. Okay. So we continue. If you continue, we get a result like this. And finally, we'll see that the difference between this and this is x3, right? This is x3, third iteration. This is x4, fourth iteration. This is x5, fifth iteration. This is x6, sixth iteration, and so on. Okay? So only when the difference is small, you stop. So your final result is here. Okay? The process is repeated till the change in variable within the designated accuracy. Okay? That's known as tolerance. So this is the basic of Gauss-Siedel method. Now this is I have taken from Harisa's book. Okay? So how the convergence happens is not important, only for reference as given here. Okay? How we are converging. So as you see here, you can have different solutions. Here one solution, here another solution, as you said right here. Okay, we can have different solutions, but it depends what is our feasibility. Okay, depending on the context. For example, voltage, you get the result per unit 1.05. Accept. Now suppose in the load flow solution you get a voltage which is 5 per unit. That is 5 times the rated value. It's not a feasible solution, so you reject that. Okay. Now, here what we have done, we have simply used the Gauss-Siedel iteration. Okay. So we have taken 7 iterations to reach the result. Now there is a way you can reach the result with fewer iterations. Okay, that is known as acceleration factor. So using acceleration factor, you will accelerate the convergence process. So that process, when you reach the result, is known as convergence process. It's known as convergence. Okay. When the difference between the final result and the previous step's result is very less, 0.001, 0.10 to the minus 4, like that. So this is known as convergence. So the convergence can be accelerated by means of an acceleration factor. Okay. For example, you can reach your career objective faster. So if you get a good guide, if you prepare on your own, you will be reaching there, but you might take 7 years. But if you get a proper guide, within 3 years you might reach your goal. Okay? That is what it means. Okay? We need proper guidance. So this is a kind of guidance, acceleration factor. It's kind of motivation, guidance, encouragement factor like that. So this is the acceleration factor. Write down this equation only. Okay? Only write down the equation. Okay? And we have been using this in the code that we will run in the lab. Okay? Write down this equation. Power system operation and control is very, very important from gate exam perspective. Okay. If you are not planning to work in the electrical engineering sector, then you have to pass the exam, BTech exam. But if you want to do higher studies or if you want to work in the power sector, PSOC is the subject. Okay. It is the convergence of all the subjects, you can say. Okay. So here, if we use alpha equals to 1.25, we will get the result in only 5 iterations maybe. Okay. But then, it's a very interesting thing. A very large value of alpha may result in overshoot. Okay. If you are too enthusiastic, you will make mistakes. Overshoot. And also, if you give a very small value of alpha, then you reach the result later. Okay, at a later time. Why a very large value of alpha results in overshoot? Because it can increase in the number of iterations. Solution might even diverge. The solution will diverge. So if you are, for example, there is a social media influencer, if you are following them very sincerely, okay, then you may divert from your goal. Okay, so you have to take everything with a pinch of salt. Okay? Take all the advice, but use what is relevant for you. Okay, it's kind of that. Now for that is the basic Gauss-Siedel method. Now we use the n-dimensional version of the Gauss-Siedel method. So we have used only one equation. Okay. So here we have n variables x1 to xn. Okay, we have n variables. Just like in a power system we can have 30 buses. So we have 30 bus voltages. So it's a 30 variable problem. Okay. So f x1 x2 xn is c1, f x1 x2 xn is c2. Like that we have n equations. We have n equations. Okay. This is again step 1 in the first form fx equal to 0. Second form we write it in the form of x equal to gx. x1, x2. Consider these are voltages which are a function of p, q, okay, all this p, q and y, p, q and y, right? So these are p, q and y, and also the bus voltages. V2 is dependent on V1 is dependent on the V1 in the previous iteration. Okay. Then this is first step, second step, and in the third step we start with the initial guess. There we had only one guess, x0, but here we have a vector of initial guess, x10, x20, x0. Okay, so you write down of this three part. Okay, 1, the basic form of equations. 2, x equals to gx form, and 3, the initial case. Only these 3 you write. This is the n-dimensional case which will be directly used for power flow solution. Okay. Right? Quickly write. Okay. The next steps are iterations. What are the next 2 steps? Iteration, convergence criteria. Initial equation, converting into x, gx form, initial guess, then iteration, and finally convergence criteria. Okay. Okay, fine. So now we'll see how it is applied to power systems. Okay. So in power systems, we have the various variables. We have discussed bus variables, voltage angle. That means this will be V delta P Q. Okay. What else? Okay, Z. But Z is not a variable, so we will. Okay, it's not a variable, so it is a function of all these 4. So we'll see the details here. So this is, I have written directly the formula for Gauss-Siedel method. So as you see here, so our objective is to solve for the voltages. Okay, so voltages can be solved using this formula. Okay, Pi scheduled, Qi scheduled by Pi conjugate K. What is Pi, Qi? These are the load demands at the buses which are given. You make the initial guess for the kth voltage. Generally, we start with the flat start. This is known as a flat start. Don't write this. First start. It is 1 0. That means 1 per unit magnitude, 0 degree delta. We start with a flat start for all the buses. That means Vj also K is also the same. Okay. Then this is the line parameter. Okay, this is the line parameter. Then we separate out P and K. We compute. But then what is the problem with this formulation? That we are using directly the line admittances. Okay. We are directly using the line admittances, which is not desirable. So we will use Y bus. So that is easier. We compute the Y bus and we will use Y bus. So this can be converted into Y bus form. Right? So we will write that. Yes. Gauss-Siedel method using Y bus matrix. So these 2 formulas you write down. These 2 formulas you write down. So this is what is implemented in the code. This formula is implemented in the code. Okay. So as you see here, the voltage in the k plus 1th iteration is dependent on the kth iteration. Okay. And it uses both the diagonal elements as well as the off diagonal elements of the matrix. Right? This uses both the diagonal and off diagonal elements of the matrix. Then, after computing the voltages, after all the iterations are complete, we can compute. This is, we can also iterate with respect to Pi and Qi, but this is not required. This will be used in your Newton-Raphson method. Okay. In the Gauss-Siedel method, we are going to iterate only on the voltages. So write only this formula. This is the working formula for Gauss-Siedel method. Okay. You see one or two problems. Can you write this one? Only write this formula and highlight it boldly. This is what will be required for solving the problem. In the exam, you will be asked problems on Gauss-Siedel, not on Newton-Raphson or fast example. Okay. Newton-Raphson only theory. But for this, one problem will be asked, at least for the first iteration. Okay. Now, quiet. Some aspects of the Gauss-Siedel method. Right. Those who are not written, right? I'm showing this again. Those who are not written, right? Only the first. Okay. So what are the various aspects of GS method? Under normal operating conditions, the voltage magnitude of the buses are in the neighborhood of 1.0 per unit or close to the slack bus voltage. That means under normal conditions, the voltage are rated. So whatever in the result you will get is slight variation, 1.05. 1.15 maximum. Okay, in that time. Voltage magnitude at the load bus is somewhat lower than the slack value depending on the reactive power demand. Why? We know that everywhere there is load, the voltage reduces. So it should be around 0.9, 0.97, 0.98 in the load bus. Also, phase angle of the load buses are below the reference angle according to real power demand, whereas that of generator buses are higher. Okay, from generator, I told you the only factor that is responsible for power flow in the circuit is the load angles, not the voltage magnitude. So load angle at the generation side should be higher and the load side should be lower. Okay. For the PQ buses, the real and reactive power are known and 11 is solved for real and imaginary components of the voltage. So for the PQ buses, after getting the voltages, okay, every iteration will solve for PI and QI. Okay, every iteration will solve for PI and QI. For the voltage control buses or generator buses, where PI scheduled and the voltages are specified, first UI is solved, then voltage is solved. Because you cannot get this for a PV bus. Hey, all of you. It's a very important point. For PV bus, this is not known. Generator bus, the reactive demand is not known because the generator doesn't know how much to generate unless the real power is specified, demand is specified. Okay. Therefore, we first calculate the reactive power, then we calculate the voltage. That is the difference with respect to the PV buses, which are only generator buses, which are very few. Suppose there are 1000 buses, only 10 buses will be generator buses. Okay. In conventional systems, in conventional power systems, when we say renewable integrated power systems, scenario is different. Okay. Then, okay. Now this is known as the polar form. You know, complex magnitude can be represented in polar form and rectangular form. Polar form is magnitude angle. Rectangular form is T plus J cube. Okay. So this can also be represented in the form of rectangular forms. Okay. And we can compute the voltage magnitudes in this way. Okay. That's it. Okay. Then rate of convergence. As we discussed, rate of convergence can be changed or increased by selecting an acceleration factor. Okay. The rate of convergence is increased by applying an acceleration factor to approximate solution obtained from each iteration. Okay. So we accelerate. Okay. A typical value of alpha is 1.3 to 1.7. This can be a short question somewhere. You write down. Typical value of acceleration factors are 1.3 to 1.7. Typical values of acceleration factors are 1.3 to 1.7. The iterations are continued until changes in the real and imaginary components in the bus voltages between the successive iterations are changed. So you see separately, or you can directly see through the polar form. This should, whether this is converging or not. If this is 0.001 general acceptance 10 to the minus 3, then we say that the solution has converged. Okay. The voltage accuracy in the range of, okay, here it is saying 10 to the power minus 5. Okay, see 10 to the minus 5. Then once the solution is converged, so this is very important, you write down this. Once the solution is converged, the net real and reactive power in the slack bus are computed from the 12, 13 equations. Okay. So once you know the voltages, compute the real and reactive power. Okay. And then what is the final solution that you will show to suppose the planning people. Okay. Suppose you are working with the PSOC, cost of operation corporation, and you are given a task of solving the load flow equation. So what you are going to show them? Will you give them all the details speech? You know. You give them the snapshot of the system where all the power flows are mentioned in each of the lines. And a simple thing is like this. Okay. So you show what is the power being flowed in the line. So only current is shown here for computation of the power. Once you know V, using YI, you can compute various powers in the circuit. This is from the Harisaran book, only for reference. Line flows. You need to compute the line flows. Write down. The final step is computation of line flows. The final step is computation of line flows. Okay. And line flows, how they are computed? By means of complex power equation. So the line flow from bus I to bus J is given by VI IIJ conjugate. SJI is equal to VJI conjugate. That means the power flowing from I to J and J to I. Now losses are given by this equation. Ideally, what is the value of this? Sij plus Ji. What is the ideal value of Sij plus Ji? 0. Okay. If there are no losses in the transmission line, whatever is transferred there is negative of whatever is transferred in the other direction. Okay. But there are losses. So to find out losses, you simply add this. Okay. This is the whole of Gauss-Siedel method. You might be asked a theoretical question. Explain the Gauss-Siedel method of power flow solution. Then you need to write all these things. Okay. Or you might be asked a problem. Yes.
So why is the losses in two directions? Like, are the losses possible to be different in either direction?
Losses are not in two directions. Losses are in one direction only.
So it's Ij and then Ji.
See, Sij should be equal to minus of Sj, isn't it? So Sij plus Sj should be 0. But if it is not 0, that means that is the loss. Okay. So this is the first question on Gauss-Siedel method. So you are required to solve all these three. This might be asked in the exam. These are small questions. Okay. Okay. There are only three questions given here. Okay. One is from one group from K. Umarao book. The first one. Okay. The rest two are from NPTEL course. Okay. The rest two are from NPTEL course. Solve all these three. Okay. because in exam it might be asked for a long question. This is generally asked as the 8-mark question. If you are asked a Gauss-Siedel solution, it will be 8-mark question, not a 4-mark question. Okay? Or you might be asked, like, for the first 4 mark, you will be asked write the formula for iteration and PQ formulas, which you are going to use in the next step. Okay? So these 3, I will just go to the solution. Okay, you have to do it at home. Try to learn the use of calculator for computing polar form. Okay? See, in the first case, we are using the same formula and we are iterating. So this is implemented in one of the codes in your lab. This is one program in your lab. This is implemented in your lab. The same thing. It's a very small code. Okay. So if you do it manually, you have to use what is the voltage at the zeroth iteration, first iteration, second iteration, and so on. Then you compute current. Then you compute the power flow. Now you sum S12 plus S21, which is only reactive power loss in this particular case. In this particular case, there are no real power loss because we have not taken the resistance. We have not taken the resistance of the line. Okay. Now these two are from NPTEL course on power system analysis by Professor Devopriya Das of IIT Kharagpur. So this one 1.3.2 and 1.3.3. Okay. Okay. This is actually I have written as part 3. This is 1.3.3. Okay. So you solve it in detail.